objectives of the project are first to meet short, medium, and long-term industrial objectives in terms of competitiveness and environment constraints. So, as I said, by reducing development time and cost of these multidisciplinary optimization methods, including also manufacturing aspects, and also, as I said, by designing more efficient configuration with better multidisciplinary compromise. So, in more details, in practice, so the objective was to address the needs of our industrial partners by extending the scope of multidisciplinary optimization by including IFE simulation like CFD, CSM, CAA, or CHT, so for aerodynamics, structure, acoustics, and thermics. One of the main objectives was, so the project was mainly focused on the adjoint capability. So the objective was really to fully exploit the adjoint capability to solve a design optimization problem with many design parameters. So we speak here about 100 or even 1,000 of design parameters. One of the key points also in optimization and in multidisciplinary optimization is the reliability and the robustness of the complete process. And one of the main module or the main part of when we speak about adjoint-based MDO is the reliability of the adjoint solver. So we have also working on this topic. And the next point, the last objective was to extend the scope of MDO to try to include in the most efficient way manufacturing criteria in the optimization problem early in the design phase. So to demonstrate the benefits of adjoint-based MDO, we decided to focus on three main topics or three main pillars. So the first one is on airframe. We decided to mainly work on wing fuselage aerostructure interaction on classical wing configuration. Then we decided to focus on airframe engine interaction. Here the main focus was the coupling between aerodynamics and acoustics, and we had some test case regarding the design of air inlet, propeller, or fan blades. And then we decided to focus on different engine components, the design of these different components, which are fan and high pressure turbine, which have very stringent aerostructure or aerothermal interaction. In order to measure the success of the project, we have defined at the beginning of the project what we have called success criteria. And these success criteria were defined following three main pillars that are capability, efficiency, and usability. So I will really briefly describe these 7 success criteria here, as tomorrow for the final presentation, I will try to summarize the main achievement of the project following these different success criteria. So the first one, when we speak about adjoint-based capability, is of course our capability to have adjoint solvers of multiphysics problems. And the challenge here was to verify the sensitivity obtained by this multiphysics adjoint with a very limited error in terms of for the gradient. The second success criteria was about manufacturability and how to integrate this new discipline or these constraints in the design process. The third one was about the exploration of the design space. As we are using the adjoint, we can have many design variables. And so the idea was to try to test different parameterization strategies to see if we were able to further improve the performance of the optimal configuration using innovative parameterization techniques. The second pillar is efficiency. So as I already said, we need robust adjoint solver when we pair for multidisciplinary optimization, but we also need efficient solver to have running time compatible with the industrial development time. So the fourth success criteria was about fast and robust adjoint-based multidisciplinary optimization capability applied to industrial test case. So here we have to, the idea was to test and monitor how MDO solver behave on HPC systems. And also we made some study regarding mesh morphing methods, if they are really compatible with an important number of cores when we are performing HPC, when we are using HPC. The fifth criteria was about industry compatible development time. So how can we reduce and how much we can reduce the development time of MDO when we have to couple several disciplines together. And the objective was to try to find solution to reach a factor of 10. And the last pillar is usability. So usability means first regarding the parameterization. So to have a physics-based parameterization that can be used with a graphical environment that can facilitate the use of this different parameterization technique by the designers. And something very important also is a link with the CAD. So the criteria here is really to try to focus on the need of the industrial partners and to have parameterization techniques that are compatible or suitable with the engine designers or aircraft designers. And the last success criteria was about MDO formulation. How can we define appropriate end user MDO formulation to fully exploit the shape, the gradient we can obtain using the adjoint approach, and adapt it to aircraft or engine design. So the idea here was to couple different kind of MDO formulation using a couple adjoint MDO or not, using sequential or uncoupled single objective optimization. So here was a summary of our 7 success criteria. Then I will give some, describe briefly the concept of the project. So in order to achieve our objective, we focus on synergy between what we call enablers and demonstrators. So enablers are the methods and tools which are required to apply our multidisciplinary optimization problem. So the different modules we have to couple together in the complete process. In the case of MADELEINE, so we have focused on 7 of them. So the first one is, of course, the multiphysics adjoint solver. The second one is MDO formulation. The third one is the parameterization. And among this parameterization technique, we have also a part dedicated to topology optimization. Then we have mesh deformation techniques. We also, as I already said, work on the HPC capabilities of the different process. And then on the manufacturing modeling and how to integrate manufacturing criteria in MDO process. And we have already, in order to apply all these enablers, we have defined 5 demonstrators. So 5 demonstrators are test case representative of multiphysics industrial.
Il faut faire une 3, 2, 1. Rajouter une version linéaire. En fait, en fait, il manque une dépendance dans la déclaration.
Sorry, François, I think we can hear you.
I'm muted. It's okay.
Okay. So for these 5 test cases, the first one is aerostructure wing design. So with 2 configuration, a long-range aircraft configuration and a business jet configuration. Test case number 2 is aerostructure manufacturing fan design of a low-pressure fan. So test case number 3 is aerothermal manufacturing for turbine blades. Number 4 is aeroacoustic propeller design. And number 5 is coupled aeroacoustics, air inlet, and fan design. I will say a few words about them in the next slide. So in more details for these 5 test cases. So the first one, as I said, is aerostructure aircraft wing design. So the challenge here was to be able and to develop all the framework to perform aerostructure flexible wing optimization of a representative modern transport aircraft using industrial tools, especially for the parameterization or for the CFD and adjoint solvers. So the strategy was to apply different adjoint solvers, so starting from the aerodynamic, and integrating progressively more discipline or more physics in the process. So by doing so aerodynamics, then aeronautic, and then optimization to really measure the impact of multiphysics phenomena on the optimal performance of the different configurations. So we apply it, as already say, on a large passenger aircraft configuration, so provided by Airbus, the XRF1 configuration. So Airbus, Onera, DLR, and IRT work on this configuration. And the second configuration was a business jet configuration, so provided by Dassault Aviation. And so Dassault Aviation, ESI, and National Technical University of Athens worked on this configuration. The second test case was to ask for the wing to perform aerostructure, fan blade design or optimization of a UHPR model engine. And the challenge was also here to include manufacturing criteria in the design process. So the strategy, as for the first test cases, was to progressively include the new disciplines in the optimization process, and also to include the manufacturing aspects in the MDMO process to avoid the accumulation of important deviation in the process or in the optimal shape that could cause important deviation in terms of performance from the design intent that the optimization process can provide. Here, in this case, we have defined three different configurations with 3 levels of complexity, starting from NASA Rotor's 37 configuration, which is a very open configuration, to a very complex industrial geometry provided by Rolls-Royce. And all these configurations were representative of low pressure fan. And so for this test case, Rolls-Royce, University of Sheffield, and University of Cagliari worked together. The third test case is, as I said, aerothermal manufacturing turbine blade design. So here the challenge was slightly different, as the focus was mainly on the aerothermal coupling by adding also some manufacturing constraints in the design process. Regarding the strategy, the first objective was to test the use of topology optimization to see if we were able to further improve the performance of the configuration using this new parameterization techniques. Or at least it is a new field of application. And the second objective was to integrate specific uncertainty or specific deviation from the initial shape in the NDO process to perform a robust design optimization of this representative turbine blade. So as for the fan test cases, we have defined here 3 different levels of complexity, from generic configuration, so NT1 here, to complex industrial geometry provided by Rolls-Royce. And in this case, Rolls-Royce, University of Sheffield, University of Cagliari, ESI, Optimad, and National Technical University of Athens worked together on different configurations. Regarding the aeroacoustic problems, so the first one is aeroacoustic propeller blade design. So the idea and the objective was to design a propeller blade considering at the same time aerodynamic and acoustic performance. So we have defined, our strategy here was to, as for the previous test cases, to try to use some advanced parameterization techniques in order to really open the design space. So we try here to use vortex morphing approach, where we have a very, very large number of design variables, several thousands. And the idea was also to test and compare the unsteady adjoint capability applied to acoustic problem to see what is the added value of this unsteady adjoint compared to a steady, more classical steady adjoint. And so for this, we have used a generic design that comply with the requirement of an CTOL or VTOL concept. So it's a light propeller that was provided by Onera. And so the partners here are working together are Onera, NLR, and Technical University of Munich. And the last test case is aeroacoustic air inlet and fan blade design. So here the challenge was slightly different, as we decided to perform in parallel the design of the air inlet and of the fan blade of this UHBR configuration. So two partners were working on the on one side on the air inlet, on the other side on the fan design, and they use a specific approach and specific interface to change our data and to make this coupled adjoint-based optimization. And as for the previous test case, here the objective was to apply steady and unsteady aeroacoustic adjoint to improve both the aerodynamic and acoustic performance of the configuration. So here we use the Vital fan blade geometry, so provided by Rolls-Royce, and a generic air intake adapted to this Vital fan geometry was used for this problem. For this test case, so Rolls-Royce, University of Southampton, and National Technical University of Athens worked together. And so this is my last slide to introduce the project and to give you an overview of the project and what we have done. And so in the coming presentation, we will give more details about the result we obtain for these different enablers or demonstrators. If you have any question, I think we can take probably one or two questions. Dominica, do you see some question on Slido?
No, for the time being, the participants are being shy, so Slido is empty for now. Don't hesitate to post your question, okay?
So if you do not have any question, I will propose to skip to the first technical presentation that will be given by Varvara Asuti from National Technical University of Athens on behalf of Professor Giannakoglu.
Thank you, Mikael.
So Varvara, you can share, I think, your screen.
Yes. So, can you see my screen?
Yes,
Perfect.
we can see the PowerPoint. If you can, yeah, put the presentation mode. Perfect. Thank you, Barbara.
Okay. So, good afternoon. My name is Varvara Asuti, and I'm a research officer at the Parallel CFD and Optimization Unit and the Lab of Thermal Turbo Machines of the National Technical University of Athens. On behalf of Professor Giannakoglu, I will present you the work of our group in the framework of the MADELEINE project. PCOpt was involved in the development of continuous adjoint methods for multidisciplinary optimization problems in the areas of aeroacoustic, aerothermal, and aerostructural optimization. This presentation covers the first two topics with selected applications, while the third one will be discussed by Dr. José in the next talk. Backbone of all the developments was the in-house GPU-enabled software PUMA and its continuous adjoint. PUMA implements a vertex center finite volumes technique on unstructured hybrid grids. Its distinguishing feature is the use of the so-called mixed precision arithmetic technique. According to this, though all quantities are computed in double precision, the left-hand side is stored in single precision, which results in reduced memory requirements and increased efficiency of the software. In the field of aeroacoustics, PUMA was coupled with an acoustic analogy, giving rise to a hybrid tool able of computing aeroacoustic noise radiated by bodies within flows. Herein, the permeable variance of the Fox-William and Hawkins analogy was used, and the adjoint to this hybrid tool was developed. The idea of the hybrid tool is as follows. The unsteady Reynolds average Navier-Stokes equations are solved in the near field. This is the red CFD domain. Inside this domain, we are placing the Fox-William and Hawkins surface, dashed black line, which includes the sources of noise. In our case, the Fox-William-Hawking surface coincides with a grid surface that does not change during the optimization. During the unsteady solution, monopole, dipole, and quadrupole terms at the Fox-William-Hawking surface are computed and stored. Then, the Fox-William-Hawking's integral can propagate the noise at any receiver location at the far field. In the problems built in MADELEINE, the objective function is the total energy contained in the spectrum of sound pressure at the receiver's location. The development of the continuous adjoint is the standard one. We define the augmented objective function and differentiate it with respect to the design variables B. Difference in the case of acoustics is that the field adjoint equations have additional source terms on the Fox-William-Hawking surface nodes. These terms result from the differentiation of the acoustic analogy. Though not shown in this slide, the continuous adjoint solver includes the adjoint to the Spallard-Talmaras turbulence model and the adjoint to the iconal equation computing distances to the wall. The acoustic shape optimization flowchart is summarized herein. The first row describes the primal solver and the second one the adjoint solver. Once the Fox-William-Hawking's integral and the objective function is computed, we proceed with the computation of the source term, the solution of the adjoint equation backward in time, and the computation of the sensitivity derivatives. Then we can update the design variables using any descent method, and of course update the shape and the computational mesh. In MADELEINE, the hybrid tool is applied to the acoustic shape optimization of a turbofan intake. Intake geometry provided by Rolls-Royce and the pressure distribution at the fan inlet by the University of Southampton. The engine is not included in the optimization and manifests its presence through this boundary condition. Given that this is an axisymmetric geometry, the CFD mesh consists of a single blade passage, and instead of running the unsteady equations, we are solving the steady state equations in a rotating frame of reference. The unsteady data required on the Fox-William and Hawking surface are reconstructed by rotating the steady field. For the optimization of the shape of the intake, practically its generatrix is parameterized using 15 control points, resulting to 26 design variables in total, since the first and the last points are not allowed to vary. In this case, the noise objective is defined at the blade passing frequency. Before proceeding to the optimization, the primal hybrid solver was verified against the expensive unsteady Reynolds average equation solver. To the right of the slide, for 3 receiver locations, you may see that we have a good agreement in the pressure perturbation. So, first optimization run, we are placing a single circumferential row of receivers in a specific angle. So in this case, the objective function is the summation of the contribution from all the receivers. We are performing the optimization for about 12 optimization cycles, and we come up with a reduction in the objective function of 70%, which corresponds more or less to 10 decibel decrease in noise. However, this reduction is directional, if you see the directivity plot, and it occurs only close to the position we have placed the receiver. So, we decided to perform another optimization run using 3 circumferential rows of receiver. These are shown in blue, black, and red on the right. By repeating the optimization for 12 optimization cycles, in this case, we come up with a reduction of 20% in the objective noise, which is practically 2.5 decibel. Surprisingly, the optimized geometry has also better aerodynamic performance compared to the initial one. Its total pressure losses is lower than about 0.12%. I'm saying surprisingly, since we never included such an aerodynamic objective in our optimization run. Comparison of the geometries from the aeroacoustic runs presented and of our aerodynamic computation, which was not shown, are summarized herein. At least in the case of our acoustic optimization runs, the most noticeable change in the shape occurs in the intake lip, which is towards the fan inlet. In the area of aerothermal optimization, PUMA was coupled with a heat conduction equation solver. The latter and its adjoint was directly developed and programmed on GPUs, and it's now part of the PUMA software. Among the various cases studying within MADELEINE was the aerothermal optimization of the C3X internally cooled turbine. The blade is parameterized using a 7x3 volumetric NURBS control grid. Depending on the optimization study, the blade shape, the cooling holes, or both are allowed to vary. In case of the cooling holes, the radii remain constant. Only the position of their center is allowed to change. For this case, before proceeding with the optimization, a series of CHT analysis, 3D, 2D, using the Spallard-Talmaras and the K-omega SST turbulence model were carried out. In the bottom, you may see comparisons of the pressure, temperature, and heat transfer coefficient with respect to their reference values, where we are comparing our computations with the experimental results. The agreement is good, assuming that for all these studies, we didn't use any transition model. The reason is that for this case, it was decided to run the optimization with the Spallard-Talmaras model and without any transition model and its adjoint. In the development of the continuous adjoint for conjugate heat transfer problems, we have the part that depends on the fluid domain, which is the blue part. We have the mean flow equation, the turbulence model, the distance equation, and the part that depends on the solid domain. This is the red. Depending on the optimization study under consideration, one or more objectives are defined and used. Regarding the coupling of the two solvers, the temperature fields computed by the heat conduction solver are imposed as boundary conditions to the flow solver. Then the flow solver computes heat fluxes on the fluid-solid interface and send them back to the heat conduction solver. A similar coupling for the adjoint temperature and fluxes is used by the adjoint solver. When developing adjoint methods, we used to check the sensitivity derivatives vis-a-vis to the finite differences, which is the reference for us. In this slide, sensitivity derivatives of 4 aerodynamic objective functions, namely the blade force, the total pressure losses, the inlet capacity, and the mean temperature over the blade surface are shown. This 2x2 matrix corresponds to the figures shown to the right. Each figure presents three curves: the finite differences in red, fully differentiated turbulence model, adjoint, in blue, and the adjoint with the frozen turbulence, which is a usual assumption made when developing continuous adjoint. The agreement of the adjoint with fully differentiated turbulence model with the finite difference is excellent. In the case of the frozen turbulence, for some objective functions, differences may be observed in the values of the sensitivities. These differences become important in the case of a conjugate heat transfer problem. For the CHT, the objective function used are the heat flux, the mean temperature at the fluid-solid interface, the mean and the highest temperature inside the blade. Here, these figures have an additional curve where we are checking the effect of frozen distance over and above to the frozen turbulence assumption. This is the purple curve, and you may notice that here, apart from differences in the value of the sensitivity, we have also differences in the sign of the sensitivities, which is very bad when working with a gradient-based optimization algorithm. So the message is that we should avoid making the frozen turbulence and frozen distance assumption. The first CHT study targets at the minimization of the total pressure losses, the minimization of the maximum blade temperature. This is handled as a single objective optimization problem by appropriately weighting the objective functions. In this case, only the blade shape is allowed to vary. Using different sets of weights, we come up with the front of non-dominated solutions, which is shown in red. The two Pareto edges are compared with the baseline geometry, which is shown in the top of the slide. For instance, for the solution that corresponds to the minimum, that minimizes the maximum blade temperature by 6 Kelvin, we may see that the shock wave increases a lot the total pressure losses. A second CHT optimization study in 2 steps is also performed and presented. In the first step, the target is to minimize the total pressure losses subject to constraints on the inlet capacity and the flow turn. In this step, both the shape of the blade and the cooling hole position vary. Once this step is completed and we have minimized the total pressure losses, we are fixing the blade shape, and we proceed with the second optimization, aiming at minimizing the maximum blade temperature. In this step, only the cooling hole positions are allowed to vary, with constraints that the cooling hole should not be very close to the blade contour. Summary of the results is shown here. Starting from the baseline geometry, we are moving horizontally to decrease the total pressure losses by about 21%. And then we are fixing the blade shape, and we are changing the cooling hole location, and we come up with this optimized geometry. It's the blue shape vis-a-vis to the red shape, which was the initial one. You may see at this point fully dominates the previous front, and the main reason for this is that we have a completely different design space for this run. the resulting geometry. You can see the new cooling holes location, which results in 30 Kelvin lower maximum temperature, mainly from the part from the trailing edge, which is the most important part when working with turbines. In the aerostructural optimization, PUMA was coupled with a structural analysis tool, and in specific with the VPS software of ESI. In this case, we also performed the development of the continuous adjoint of the coupled solver. Adjoint-based aerostructural optimization studies were performed in a business jet. The results from these studies will be presented in the next talk by Dr. Gilbert Roset from Dassault Aviation. Closing, on behalf of the NTUA group, I would like to thank the MADELEINE project for giving us the opportunity to work on multidisciplinary adjoint methods and apply them in real-world cases in the fields of aerospace and turbomachinery. Our findings in MADELEINE using PUMA for compressible and even transonic flows reconfirmed findings using incompressible flows using the OpenFOAM software developed and made publicly available by our group. So in case you are working with adjoint methods and you wish to keep a message, this is that you should solve the adjoint to all governing equations. Avoid making assumptions such as the frozen turbulence, either in a monodisciplinary or, and most important, in multidisciplinary optimization problems. Thank you very much.
Thank you, Barbara, for the presentation. We can ask to the audience if you have any question. We have time to take question.
I cannot see the questions
No,
right now.
No. Is there any question among the participants? I think you can directly ask the question. You can unmute. I guess it is possible.
Yes, we have quite a lot of time. We have 10 minutes before the other presentation, so maybe don't hesitate to unmute yourself to ask questions. And during Barbara's presentation, some participants send messages via chat saying that their IT settings prevent them from using Slido. So if this is your case, exceptionally, I think we can allow to ask questions via chat as well, if there are many. So don't hesitate to use either of the options, either unmute yourself and ask your question orally, or use Slido or the WebEx chat, okay? So I think there is a first question available.
Should I answer the question? Okay.
Yes. Yeah, go ahead.
CSM stands for Computational Structural Mechanics, and SPL for Sound Pressure Level. So it's two completely different things. The SPL is, we are using it for aeroacoustic optimization problem, and the other one is for the aerostructural problems, and will be discussed in detail in the next presentation.
There is one question also from Mohammad Monipiri from KTH. Hello, in the slide which you show the result for frozen assumption, there was some oscillation in the sensitivities. Are they normal?
I assume you are referring to this slide. Yes, normal, it depends on what you mean normal, in the sense that this is the point of the slide. So we want to show that for these design variables, you have a very bad sensitivity when you're working with the frozen turbulence. I don't know if you mean something different in the oscillation.
What we can add maybe here is that this is what you show, it's the value of the sensitivity with respect to design variable. So the sensitivity from one design variable to another can change significantly. And
okay, yeah, I got your point.
It's not really a fluctuation or oscillation in the numerical process, I would say. Or...
Yes. No, this has nothing to do with the optimization. This is on the horizontal axis. We have the design variable. So probably, if you remember the grid we are using for parameterizing, you may have two different design variables that are the one next to the other. So it's reasonable to have different values.
Okay, thanks, Barbara. Any other question? So if not, I propose to switch to the next speaker, even if we are slightly in advance on the agenda. Gilbert, you have 40 minutes almost.
Okay, maybe too much, or if you have a lot of questions, I hope. So I will share my screen. Did you see my screen?
Yes, we can.
It's okay. Thanks. So I will start. The work I will present has been done by 3 teams, not only Dassault teams, but also NTUA, so Technical University Athens. And the third team is at ESI, it's with Gabriel Fougeron. And what I want to show to you, it's the impact of the adjoint in aerostructural airframe optimization of a business jet. The outline is the following. I will describe the toys test case, namely generic business jet. After, I will compare rigid optimization with flexible optimization in order to know if flexibility is mandatory or not for the test case we are looking for. Next topic is robust optimization. So it deals with, of course, multi-point approach. And the last point deals with aerostructural optimization. Sorry. Our generic business jet is based on something like Falcon 2000 LXS, but it's a generic model, in fact. So not equal to the real aircraft, but close. For this generic business jet, we have compared results mainly from the 2 aerodynamics teams from NTUA and Dassault. On the right corner, you can see polar curves for the 2 teams for 2 flight points. The first flight points, the flight points devoted to jig shape. It's Mach number 3.82 and angle of attack 2.5 degrees. It is a changing flight point, and the second one, P2, it's a Mach number 0.8 and angle of attack 2 degrees. On what we want to optimize is the shape of the wing. In order to do that, use a CAD modeler, and we have some aerodynamics parameter, twist angles for master section, control section, and for trailing edge camber parameter. Of course, we want to have to trim, and in order to perform trim, we use HTP rotation angle. Sometimes we add also angle of attack in order to achieve lift coefficient prescribed. We want to obtain lift coefficient constant or superior or equal to given value with a certain accuracy. Accuracy is 10-4. Something for trimming constraint. We want to obtain a pitching moment equal to 0 with epsilon equal to 10-4. You can see on the corner here, camber effect and twist effect on the wing of the business jet. At Dassault, we have the CFD solver Aether. Aether is based on Galerkin least square approach. You can also say Petrov-Galerkin, streaming out prime. And Aether is able to solve a lot of equations, but we will focus here on Rand's equation, Reynolds average Navier-Stokes. And we select one of our turbulence model, Spallard-Maras. Of course, we work on HPC, and for this kind of platform, we use MPI and domain decomposition. This software, Aether, has been fully differentiated using automatic differentiation using Tapenade INRIA software. So it's a discrete adjoint. Our gem at Dassault is the CAD modeler Ganymede. Ganymede has been built by my colleague Stephen Kleinwand. It was a 20 years work, and is fully differentiated and able to manage all the parameters needed by an aerodynamic engineer, like sweep angle, twist angle, camber, and so on. Puma code has been present by Barbara from NTUA, and at the opposite of Dassault code, the choice here is a continuous adjoint. The turbulence model is also Spallard in order to have the same kind of results both for Polar and CP. And it's a fully optimized code on GPU. On this slide, some comparison have been done. What we want to demonstrate here is that it was needed to differentiate the turbulence terms, so here the Spallard-Maras, in order to obtain accurate results. We compare for different variables. We have 9 variables in this case, 4 twist angle plus rotation angle of HTP, variable 9, and variable 5 to hide the camber parameter, and we compare both results obtained using finite differences and adjoint, with and without gradient of turbulence, and with and without flexibility effect. I will explain what I have in mind, flexibility effect. Mainly what we can show on this slide is that for the changing test case Mach number 0.82, it's OP1 test case, it was mandatory to add gradient of turbulence. If you don't add this turbulence gradient, it is possible to have not only a bad value for the absolute value, but also a different thing compared to finite differences. And the second point is a flexible effect for gradient. Could be not. On this slide, you have a comparison of rigid optimization for the OP2, so for Mach number 0.8, comparison between Dassault result and NTUA result. In both cases, we obtain a gain of 2% on drag coefficient. And we have two constraint on pitching moment and lift coefficient. They should be equal to datum. Constraints have been achieved with 10-4 accuracy. And so we have quite the same gain and quite the same optimized variable. In blue color, it's the result for NTUA, and in red color for Dassault. So both for the ninth variable were close to the same value. I have to introduce more operating point we want to run. Operating point 3, this is supposed to be the same as operating point 2, but without the twist parameter. Twist parameters are frozen to 0. The operating point 4, it's a point where we want to optimize camber, but also angle of attack. So we have an additional parameter. Operational point 5, it's a 2-point optimization. Yeah, first point deals with a twist angle distribution on the wing, dealing with a worst case with loads. We have for 2 points. One is with a higher loads on the inner wing and lower loads on the outer wing, and for the second point, it's the opposite. This kind of robust optimization deals with worst case approach. What we want to minimize, it's a C-sigma approach, we want to minimize mean value plus 3 times standard deviation of the drag. And of course, we have to respect lift constraint, both on for point 1 and point 2, and 0 pitch moment for point 1 and point 2. Operational point 6, it's the same as for operational point 5, but we had angle of attack parameter both for point 1 and for point 2. In order to perform all these optimization, before we perform optimization in order to have a pitching moment equal to 0. So we have performed preliminary optimization, both at NTUA, at Dassault, for single point and for robust point, multi-point optimization. On this slide, we have a synthesis of all optimization regarding Dassault optimization. We compare to datum the drag obtained for several options of optimization. For optimization 2, we obtain the best drag coefficient, of course, because we have optimization with both twist angle and camber parameter. What I want to show on this slide is the effect of robust optimization. For example, on optimization 6, you have a large decrease of standard deviation because the gain come mainly from standard deviation on the cost function. Cost function, keep in mind, is the mean value plus 3 times standard deviation of drag. Next step is deals with aerostructural optimization, because the work in this in the framework of MADELEINE, the work for Dassault and Interior was to compare flexible optimization, but also the additional work for Interior and ESI was to obtain aerostructural results. How to build the CSM model? CSM model was the job of ESI with inputs from Dassault. Inputs were close to loads prescribed for the Falcon 2000, but not exactly the same because we keep only a few load cases from 25 certification rules. And we gave also some data in order to have a realistic flexible effect in transonic domain. Keep in mind this point because in the conclusion I will go back to this point. So ESI has performed a jig-shape process and she has obtained the jig-shape using VPS software from ESI. On this slide, you have a comparison for Dassault results of rigid and flexible optimization. Mainly, it was for OP2, so for Fresnel Mach number 0.8, we have a gain of 2%, both for rigid and flexible optimization. But if you take results from rigid optimization and if you recompute this point using flexibility effect, so using a fixed point approach, the gain decreased to 1.7%. So we can, as you can show, the real gain using flexible optimization here, it's only 0.3% additional gain respect to the 1.7% using former classical way of optimize, so optimization using rigid assumption. We have performed the same thing, but for a 2 cases multi-point optimization. The cost is an average between 0.1 and 0.2, so point Mach number 0.82 and point Mach number 0.8. And here, if you compare rigid optimization in red color and flexible optimization in green color, we have mainly the same gain, 2.7% on the blended drag coefficient, the cost. of the optimization. Breakdown between point 1 and point 2 is a gain 3.5% for the larger Mach number, and the gain is not a gain, in fact, minus 0.1% for the second point. But unfortunately, in this case, if we perform flexible fixed point for the two optima obtained using rigid approach, if you compare to drag coefficient, so for the same lift coefficient and for pitching moment 0, you obtain exactly, in this case, exactly at 10 minus 4, the same drag coefficient for point 1 and point 2. So here, for this multi-point optimization, the gain using directly flexible optimization compared to former way of optimize using rigid optimization, the gain is 0. Give comment about that after. Aerostructural optimization. It was the work of NTUA and ESI. Prescription from Dassault and definition of the test case coming from Dassault. What we want to minimize is the fuel burn. You have the formula here. Fuel burn, because we want to perform green optimization, it's equal to the zero fuel weight multiply. It comes from the Breguet-Leduc formula, in fact. Multiply exponential of a composite based on velocity, lift coefficient, drag coefficient, gravity, fuel consumption, and so on. So, definition of the problem is the following. We want to, for Mach number 0.8, angle of attack 2 degrees, we want to minimize the fuel burn, of course, and we have to check and we have a constraint on lift coefficient. We want to achieve a 0 pitching moment. And we have additional parameters, not only the 4 camber parameters, triangle camber parameters, the 4 twist angle parameter, the HTP rotation angle, but also we add the leading edge sweep parameter, the delta of sweep, in fact, additional sweep, and the thickness, relative thickness parameter of the wing. Results are the following. All these optimization have been done using optimizer SLHQP. So the optimization work very well, also for this aerostructural point, and we have here the convergence of all the variables. You can notice that sweep angle is on the low bounds. At ESI side, they also plot a map in order to know what are the variation of the structural mass regarding sweep parameter and thickness parameter. It's classical, if you increase thickness, you decrease mass. It was not classical for sweep, in fact. On this slide, you have comparison of optimized shape, red color, and baseline in green color. And a movie in order to illustrate conversions of fuel burnt and of constraint and geometry, and also the event variable. To conclude, we have performed in this work rigid and flexible optimization, and we have a nice comparison between the two teams, NTEA and Dassault obtain results very close. We have performed also robust optimization and using worst case and Six Sigma approach. With robust optimization work very well. One of the conclusions for flexibility effect, because we wanted to know if flexible effect was needed or not. Lessons learned, it's in this case, flexibility was not required for cruise point. Why? Because if you compare, for example, twist angle at the tip of the wing between flight point Mach number point A2 and Mach number point 8, you have something like 0.1 degree between the two twist angle distribution. So it's a low figure. With this kind of flexibility, because the flexibility was close to real flexibility of Falcon jet, classical Falcon jet, so flexibility effect is not needed. But for our next step, we intend to work on a high aspect ratio wing in order to decrease fuel burn, and in this case, maybe flexibility will be very crucial, and work done in the framework of Madeleine is operational in our optimization group. One of the points obtained here by NTEA team is a decrease for fuel burn of 10% using full aerostructural adjoint optimization. The approach both at Dassault and for NTEA for the flexible adjoint, it was an approach uncoupled, so with a fixed point approach, both for the nonlinear fixed point, but also for the adjoint computation. From an industrial point of view, it was the good choice. And so coming back to this aerostructural optimization, the raw fuel weight has been decreased by 2%, and lift over drag coefficient has been increased by 8%. So it deals with a formula given before, with a fuel burn decreased by 10%. I want to give the opportunity of my talk to thank European Commission for funding this project, because it was a good time to compare with partners NTEA and ESI, to compare our results and to be more confident on both, for example, on gradient of turbulence, gradient flexible effect, and to know what we can obtain using aerostructural optimization. At Dassault, if we want to perform this kind of optimization, of course, we have to replace VPS by our Elfini structural code, but we have paved the way to do that, and For our next challenge, it's a green Falcon with a laminority on both upper side and lower side, on intrados and extrados of the wing, and we want to be laminar up to the shock. So for this high aspect ratio laminar configuration, I think it will be very important to take into account flexible effect. And after we have to make the link with our colleagues from structural department and to perform aerostructural optimization, because I'm sure it's a crucial point for the future. Thank you. If you have a question, I am open for question.
Thank you, Gilbert. There are 3 questions for you on Slido. So the first one comes from Quentin Bénéard from Onera. So how do you compute CD, sigma CD on slide 12 and 13?
Sigma CD. It's an empirical way of compute sigma and mean value. I compute mean value, it's the average between the two drag coefficient, and sigma obtained by I compute variance and after square root of variance, and variance is computed by I didn't give the formula on the slide. Classical discrete way of compute variance. So to add this, it's not on the slide. Okay. So it's a discrete manner to compute variance. Classical, no new to do that. It's not coming PDF if it's the question.
Probably, yes, I guess. So 2 other questions. So from Stefan Gertz from DLR. The first one is, can you explain in slide 17, the flexible optimization converge much faster than the rigid one? Why?
17.
17.
17, yeah. Difficult to explain that. In fact, it's tricky because we have to realize both pitching moment constraint and lift constraint. And yes, I agree with Stefan. Should be the opposite, maybe, but coming to constraint accuracy needed and SLHQP optimizer, and we have a precision of our solver and of our computation of drag coefficient. Far field, for example, has a certain accuracy. So you have to take into account that, and finally the SLHQPA obtains the solution with the accuracy needed for constraint, but could be the opposite. I agree, but it's only the results of the I have obtained. I think it's only an epsilon stopping criteria effect.
And so second question from Stefan, even if the gain is 0, what does this mean in terms of the optimized parameters? Are they the same as well?
Yes, I have not as backup the result, but I keep in mind, yes, the parameters are the same also. It's not two different shape who gave exactly the same drag. No, it was exactly the same parameter, in fact.
Okay.
Thanks, Jabir.
It was not the same shape if you take into account flexible effect, but if
Yep.
you orthogonalize the 2 points, it's exactly the same thing.
I see. Thanks.
And I don't know if for Airbus it was the same thing, but I hope it's the same conclusion. I know at DLR you have also performed flexibility effect, different stiffness for the wing. I think it's a good point to do that in order to show that for if you have more flexibility, it's mandatory to perform optimization using flexible gradient.
This will be detailed in the next presentation. Another question from Vitze Koopman from Airbus. What exactly do you mean by flexible in this context? Is it the deflection of the wing in vertical direction in addition to the variable twist change?
Flexibility is a flexibility of the wing. We have in 3 directions, not only z direction, but mainly it's in z direction. Yes, but it's flexibility for the stiffness matrix structure, and so you obtain a displacement with a 3 component on all the wing, and okay. As you can see here, you have the deflection. Okay, on this slide you have also effect of optimization parameter, not only flexibility. I should put the same thing on the slide to flexibility, maybe side. The jig shape, not this one. Yes, for example, you can see here, if I have no lag, flexibility of the wing. Yes, you have mainly Z effect, but you have also an effect in X direction.
Yeah, at equilibrium, you have a modification of the position, vertical position, but also a reduction of the twist at the tip. This is what we. When we do aeroelastic simulation, we change the.
Of course, we have a swept wing. So if you have a flexion, this flexion induce twist angle twist angle modification at the tip and on the for all the twist low of the wing, of course.
Thank you. Yeah, it wasn't quite sure for me if it was something in your methods where you basically have flexible gradients inside the optimizer, or if it was really the change in the structure.
In order to add flexibility, we solve the complete fixed point. So we have to solve both aerodynamics, structural, and mesh deformation. And
Yep.
It was not a question, sorry.
No, it's clear now. Thank you.
Okay. And maybe to even be more clear, we can say that when we speak about aeroelastic simulation, it is the structure is frozen. We only couple the aerodynamic and the frozen structure to have the displacement. of the wing. And when we speak about aerostructure optimization, we change the shape of the wing, but also the internal structure. And the last question, so Gilbert, so mentioned in your talk, a remarkable 8% L/D improvement, rather large. Does that meant the starting wing should have been a better design in first place?
No, it's mean in fact it's a choice problem, and we have to take into account a lot of loads for CS 25 certification, and we have also to take into account takeoff and landing points for aerodynamics, and coming to the real Falcon 2000 LXS, the optimization of the shape is a multi-point optimization with a lot of points. Here we consider only two, in this case for aerostructural optimization, it was one flight point. So it's not enough to conclude. In this case, of course, and it was my choice to use my number 0.8, but the decrease, the impressed decrease is only an artifact of the choice for the test case. But it was a nice result.
Okay, thanks Gilbert for this, for answering to all questions. So it was the last one. I think we are just on time, so we can take a break of 15 minutes and be back at 3:45, so in 13 minutes exactly. So you can stay connected and take a coffee and come back in 13 minutes. So you are ready, Joël?
Ouais, on va essayer.
Okay, so as it is 3:45, I propose to restart on time. And so our next speakers are Joël Brézion and Romain Liventi from Airbus. So if you can just say your role at Airbus and in the project to start, and then I'll let you the floor.
Thank you for this introduction. So my name is Joël Brézion from Airbus. I'm working on the digital aircraft and digital twin, and together with Romain Liventi, who did most of the work on Airbus side, we will present the results obtained within in the frame of the Madeleine project on the XRF1 aircraft configuration. So the title of the presentation is to highlight the benefit of the so-called coupled aeroelastic adjoint for optimizing the long-range XRF1 aircraft configuration. Alors, XRF1 is not the new aircraft product. It stands for External Research Forum, and it is the first multidisciplinary model that is representative of industry-relevant use case that is shared with our partners, Onera, DLR, IRT, in the frame of the Madeleine project to illustrate multidisciplinary optimization. So is it frozen? Is it frozen? Yeah. So the context of the presentation, the context of the study, as you have noticed that the drag level of an aircraft is a key driver for the fuel burn consumption, and it's utmost important to master the external wing shape, not only for a given point, but for the full flight mission. And here, the adjoint approach, as highlighted previously, is a powerful means to perform optimization and design the external wing shape. And here, in the frame of the Madeleine project, we explore the coupled aeroelastic adjoint, since it's promised to consider the aerostructural deformation that occur during the flight. So the objective within the Madeleine project was to implement and validate the so-called coupled adjoint in order to compute accurately aerostructural sensitivities and to assess the benefit of these new capabilities to perform either what we call flexible aeroshape optimization and aerostructural optimization. Romain will explain in deeper details what does it mean, what are the assumptions behind that. And to apply the methodology on an industrial representative configuration, as explained at the beginning, the long-range XRF1 aircraft model. And for that, we set up a working group where the role of Airbus was to define the use case and to perform the flexible shape optimization. Onera and DLR did similar optimization, and additionally MDO with aerostructural shape optimization, and everything with the support from IRT Saint-Exupéry on the MDO formulation, and you will see this later in the next presentation by Anne Gazex and François Gallard. And now we will present you the couple adjoints optimization overview, then the collaborative work on the gradient validation, and then the application made at Airbus, then at Onera, and lastly at DLR, and then some conclusion. And now I give the ball to Romain, who will present you what has been done at Airbus on the Airbus side. Romain?
Yes. Thank you, Joël. So first, just a word on the couple adjoint optimization framework, and in more details also the details on the different high fidelity tools that have been used by the different partners. So as for the what was presented for the GPJ group, here we are interested in flexible aerodynamic optimization and aerostructural optimizations. So basically the coupling here, we are interested in the aerostructural coupling, so that we rely both on CFD and CSM solvers to derive objective functions and constraints. And the whole purpose of the MADELEINE project was because we are targeting high dimensional problems with costly models, we need to rely on gradient-based optimization computed with adjoint. So here, there was 3 objectives. The first one was to develop the couple adjoint in the different frameworks, to validate it, and then to assess it on more complex test cases. So regarding high fidelity tools, so we use different tools depending on the different partners involved in the XRF1 test case. So regarding CFD, so all partners actually solve the Ron's equations with a fully linearized Spalart-Tolmar turbulence model. But on Airbus and DLR side, we relied on the TOW CFD solver from DLR, whereas on Onera side, they rely on their own solver called ELSA to compute flow analysis. Regarding CSM analysis, we all use the MSc Nastran, both to compute linear static aeroelastic couplings with SOL 101, also to compute load cases for partners who tackle the aerostructural optimization. Regarding structural models, so there are 2 types of application that are considered in this work. The first one is flexible shape optimization. So for this purpose, we actually freeze the structural model, so it remains frozen throughout the optimization. And we only want to assess the benefits of including flexibility effects to improve the aerodynamic performance. Whereas Onera and DLR also conducted the MDO, so here with a parameterized CSM model, which is also updated and improved during the optimizations, to assess the benefits of varying both the aerodynamic performance and the structural mass to improve the overall aircraft performance. Okay, so before tackling complex applications, we decided to perform a collaborative validation of our coupled adjoint implementations, both with respect to the Philip diffusion method, but also to perform a cross comparison of coupled adjoint derivatives computed with adjoint between partners. So for this purpose, we devised a common validation test case here on the simplified configuration of the XRF1 aircraft. So as you can see on the left-hand side, only a wing body configuration. And we tried as much as possible to rely on common inputs to minimize differences between the different partners. So for instance, we use the same validation parameterization. It was being set up with one of Airbus CAD modeler called Page. Here with the simplified validation parameterizations, so which includes both platform parameters, as you can see on the picture, so including sweep, wingspan, design variables, but also chords, and also sectional parameters. In fact, 3 sections for which we can specify the twist, the thickness, and the camber. Similarly, for the structural part, we relied on the same structural model, which was set up by DLR using their tool called CPAX-Mona. So obviously, although we try as much as possible to have the same inputs, there are some differences. So, and they are to be found on the CFD part. So both DLR and Airbus relied on the TOW CFD solver, so we could share the same grids to perform the flow analysis, whereas we had to provide structure grids to Onera to compute, so that they could compute similar flow analysis. So overall, so first each partner compared its gradients with respect to the finite difference method, and then we also perform a cross comparison of our couple adjoint derivatives. So here is an example for the pressure drag coefficient of the validation between Onera, Airbus, and DLR. But the outcome of this study is that, considering that we still have some discrepancies in our own workflows, it can be linked to CFD, but also the CFD and CSMM coupling strategy. We achieved quite a good agreement for the different aerodynamic coefficients. In fact, more details on the setup and the results are available in the AAA paper that is mentioned at the bottom of the slide. Okay, so now let's jump to applications. So first, we'll start with the application performed by Airbus. So in fact, multi-point flexible wing shape optimization of the full XR1 configuration. So first, a word on the parameterization. So here we are actually working on the jig shape of the aircraft. And because we are keeping the structural model frozen during the optimization, we also impose a specific dedicated geometric constraints. So we are freezing the planform and also the thickness of the wing for the entire wing. We also take into account another geometric constraints by freezing the leading edge radius. So in fact, here we will only consider camber and twist slow design parameter changes for this aerodynamic optimization. In total, we consider 110 parameters, which are split across 18 sections. So 15 sections are directly controlled. They are represented in blue on the picture, and 3 of them are interpolated, represented in orange here. For the twist flow, we consider only 5 control points, which act as deformation points to deform the twist flow smoothly for the entire wingspan. In addition to the wing shape parameterization, we also have an additional design parameter in order to rotate the horizontal tailplane to trim the aircraft. Now, regarding the problem setup, so here we consider a multi-point optimization in order to yield a robust aerodynamic design. And here the objective function is actually derived using a simple quadrature-based approach on aerodynamic performance, so which actually translates into a weighted sum of the different of the drag coefficient of the different fly points. We also consider trimmed CFD-CSM computation in order to impose aerodynamic constraints. So basically, and more precisely, it means that we are able to adjust both the angle of attack and the deflection of the HTP for each iteration of the process and each flight conditions to reach 2 different constraints. First, that we are able to meet a point-dependent lift target coefficient, and also to make sure that the aircraft is trimmed for each computation, so that each optimization iteration is actually made feasible thanks to this process. Okay, so these are the flight conditions considered in the problem. So 5 flight conditions. You also have in blue the different weights, which will result from the quadrature rule on aerodynamic performance. Okay, so now regarding the overall computations. So as I mentioned, we include the 5 flight conditions. So actually the high fidelity computations are performed for these 5 points in parallel in order to reduce the roll time of the process. And the overall process is managed by the multidisciplinary optimization environment GMCO developed by IRT Saint-Exupéry. Okay, so now let's take a look at an overview of the convergence of the optimization. So we are actually looking at the variation of pressure coefficient contours for the different flight conditions. And as we can see, the optimization actually requires 34 iterations in order to converge, so we can see, and yields a multi-point drag reduction of around 3.4% of the baseline multi-point drag. So beside this convergence, we are also interested in actually to have a look at in more details into the physical origins of the drag reductions. So for this purpose, we actually perform far-field drag breakdown analysis on the optimal solutions. And basically, these analyses allow us to decompose drag into different physical components, such as wave drag, induced drag, viscous pressure drag, and so on. So what you can see here on this graph, so we have actually the different flight conditions included in the problem. So 1 color per flight point. On the left-hand side, we have the overall total drag reductions achieved by the optimization. So they range between 2.4% up to around 4.7% for the depending on the flight conditions. And when we look at the breakdown, we can see that most of it actually comes from wave drag reduction and then a bit of induced drag and viscous pressure drag. Okay, so now besides this flexible optimization, what we were interested in was to find out what is the benefits of actually including couple adjoint with respect to a classical optimization process that we had before. So basically, this is what we call rigid optimization. And within this rigid optimization, we will actually neglect flexibility effects in the optimization process. So to clarify, what we do is that before the optimization, we compute the real point-dependent flight shapes using coupled CFD-CSM analysis. So that's the orange shape here. And then during the optimization, we no longer recompute the structural feedback. So we therefore only perform primal and adjoint CFD analysis to compute the functions of the problem and the gradients. This has a side effect of reducing the workload time, but obviously it's not as accurate because we are lacking the consistency for the structural feedback. Okay, so with this process, we actually perform exactly the same optimization, so 5 flight conditions with the same weights to obtain a rigidly optimized jig shape. And then from this optimized jig shape, you actually recompute real performance using CFD-CSM computations so that we can actually compare with the results obtained from the previous optimization. So we carry out the same far-field drag breakdown analysis on this, and on the left-hand side, this is the comparisons with the final results. So you have in blue the flexible optimization that I've presented previously, and in orange, the rigid optimization. And basically, what you can observe here is that the flexible adjoint is able to yield only small additional improvements. They are equal on average to around 0.2% of the baseline drags. Okay. So now I will hand the floor over to Joël to present the next results.
Thank you, Romain. So I will just present you briefly some results obtained first by Atonera. It's about three multi-point optimization scenarios to answer one of the questions that was raised just previously by Gilbert. with three different hypotheses. The first one was to consider 100% rigidity. So this means that the optimization is done directly on a fixed flight shape using without coupling and without flexible adjoint. The second one is an hybrid approach where combining aerostructural computation without flexible adjoint. So this means the gradients are rigid. And the last one, and the reason this is called hybrid, and the last one is 100% flexible. So this means that and the CFD CSM couple is performed as well, the gradients are computed accordingly. For each multi-point optimization, 3 points are considered, 3 different lift coefficients in cruise condition, and the goal was to minimize the sum of the drag with constraints on the corresponding lift. In terms of parameterization, Onera used in total 67 design parameters. So 3 parameters to control the angle of attack. So 1 for each flight condition. 11 sections, and for each section, 6 camber parameters used. So 66 parameters, plus 7 parameters to have a fine-tuning of the control of the twist. Alors, I will concentrate the next slides on these 2 pictures. On the left, it is an optimization done using .mmfd, modified method of feasibility direction that is a kind of first order constraint gradient. And on the right, an optimization performed with SLSQP, a second order constraint optimizer. The role is not to compare both optimization strategies, but rather to highlight different behavior. And in the blue, you will have the initial configuration as used as a reference. And what is plotted are the variation of the drag with respect to the reference configuration for different lift coefficients. So first, what is nice to see is whatever the strategy followed, either full flexible or rigid, in all cases, we get an improvement in multi-point. So this means that first that the multi-point optimization is working properly. But with different behavior, if we are using MMFD, where in fact we see little difference between the different strategies, while it's more spread using the SLSQP. And in fact, by doing a detailed analysis, post-processing analysis on the MMF, with this optimization in red, we observe that the optimizer mainly drive down the wave drag without touching, in fact, the induced drag. So this means that at the end, if you want, the center of lift on the wing remain the same, and in fact, you do not experience large flexibility effect. On the contrary, where the SLSQP optimize at the same time the drag and the induced drag. And this explains why we get a better improvement with SLSQP. If we look at now in deeper detail the impact of the flexibilization, so in dashed line you have the rigid optimization, but for fair comparison you need to recompute the optimized shape, rigid shape, using CFD CSM couple computation, and this is done to ensure consistency between the results. And we see that whatever the strategy, we get a light decrease of the drag. So this means that it already shows that it's beneficial to consider flexibility in the optimization. Now, the first way to consider flexibility is with the hybrid approach. So by updating the state by CFD CSM couple computation, and here we get an improvement or light improvement using MMFD, while the improvement is already better using SLSQP, which is normal because we have more flexible effect since the optimization is now on the SLSQP changing the center of lift on the wing and therefore the flexibility. And if you consider flexible CFD and flexible gradient, you get even better improvement. And a last attempt made by Onera was to see, okay, what's happened if we increase the flexibility of the wing? It's an artificial exercise, but simply by tuning the structural coefficients, they increase the flexibility by a factor of 175. And what is interesting to notice is already on the baseline configuration, we see quite a huge impact due to this increase of flexibility. And compared to the previous variation of drag due to the thanks to taking into account the full flexibility approach, now on the very flexible wing, the benefit is much important. So this means that the couple adjoints takes real benefits on a large flexible wing. Another example will be obtained on DLR on an MDO analysis. So here the objective is to reduce the fuel burn for a powered and trim XRF1 configuration where they consider at the same time wing platforms, wing thickness, the shape, as well the structural material. So this means it's the true MDO problem, considering lots of design constraints related to aircraft performance, but also overall aircraft design characteristic and structural mechanics. And in terms of workflows, in fact, what is interesting here is to highlight first that we have a unique optimizer driving the full process, which is a multi-fidelity process, CFD CSM for the cruise performance, DLM coupled with CSM for loads and structure analysis, and a ROM-based OAD constraint for the overall aircraft design constraints. And all this box provides state and gradient back to the optimizer. Okay, this is typically the convergence that is observed, and you can see that after a few iterations, we already get a large drag benefits. What is interesting to notice is, in this case, the MDO problem leads to an increase of the LBRD, so increase of the aerodynamic performance at the cost of an increase of the mass, the empty mass. We can see on the right the variation of the thickness of each element, structural element, as well an example of variation of the twist after optimization. This is an example of the bending comparison between the baseline and the optimized. It is worth notice that keep in mind that the mass also increase, also explaining the reason, the rationale why we get a higher bending on the optimized configuration. So conclusion, the aeroelastic adjoint has been successfully developed and validated, and this is really important. And as Romain highlighted, this was a collaborative work. It takes time, but it's really worth to get confidence that we have the right implementation, and it leads to a successful demonstration on academic and industrial representative configuration. What we observe in the benefit of the couple adjoint is it really helps you to get the last drag improvement compared to classical rigid optimization. And the impact of considering the couple sensitivity becomes more and more predominant as the flexibility is increasing. And this is definitely a key enabler for considering MDO problems. In terms of industrial benefit of this Madeleine project, first, the aeroelastic adjoint capability was implemented and demonstrated in industrial simulation ecosystem. So this means that we started at the beginning of the project at around TRL of 3, and thanks to the project, we went up to TRL 6. And we have now a maturity that we can say the capability now is in the hands of the aero designer, and they are using it for a real industrial application. So many thanks for this Madeleine collaboration to help us in increasing our capability in aero shape optimization. And we have 5 minutes for question. In the meantime, I show you just a nice video that was made by DLR showing the convergence of this MDO problem. Thank you for listening.
Thank you, Joël. Thank you, Romain. So, do you have any question in the audience? I don't see question in Slido.
That was clear.
There are some, Michael, in Slido.
Ah,
I don't see them. I see now. So, okay, I will start with the first one. So I don't have the name, anonym from someone. So XRF1 flexible wing shape optimization is a constraint for span-wise lift distribution included?
No. In fact, here there is no span-wise lift constraint for the pure aero-elastic optimization. On the contrary, for the MDO made by DLR, this is tackled directly by the MDO formulation. but there is no explicit center of lift constraints.
Yeah.
But this could be added if needed.
So 2 questions from Stefan Gertz from DLR. So from what I understand, both Dassault, NTUA, Airbus, DLR, and Onera compare rigid and flexible optimization using couple adjoint. Did you compare both approach and aerostructure optimization?
But the purpose is not the same between the aeroelastic optimization and aerostructural optimization. On aeroelastic optimization, the purpose is really to improve the drag performance. On the aerostructural optimization, we are not necessarily emphasizing benefit on the LOVRD, on the aerodynamic performance, but really on the MDO side. So no, we didn't compare because we are, if I understand properly the question, the comparison would mean the apple and banana, because we do not consider the same things. I hope I answer your question, Stefan.
Yes, you did. It was more rhetorical in the sense that the real thing to do is, of course, aerostructural optimization.
If you want to perform MDO, yes. Yeah, definitely. We are not claiming that with the aeroelastic optimization, we are doing MDO. The purpose is different. It's really to improve the pure aerodynamic performance under aeroelastic deformation.
Okay, so you're saying rather than doing a flight shape optimization, this would be a next step towards being more realistic.
Yeah.
Okay.
If we can formulate properly the MDO problem, yes, definitely. Yeah.
And the last question from Acronym also. So understanding that Nastran is an industrial certified tool, have you considered using a different CSM source code to enable better integration with your tools?
Alors, no, we concentrate on the Nastran because it was the common tools used by all 3 partners. But normally the formulation of the problem is such that it should be solver independent. So if we want to use Abacus, as long as it provides all the information, we could replace Nastran with Abacus.
We can even use our own model if you want for the structure. What we need for the aerostructure optimization is a parameterized model.
Yep.
And for elastic optimization, we do not need a parameterized structural model. We just need a model.
A frozen model, in fact.
Yeah.
Thank you. So we are on time.
Yes, just on time.
Perfect. Thank you for listening.
Thank you, Joel. Thank you, Romain. So I propose to switch to the next speaker. So as mentioned by Joel, here the presentation will be dedicated to the work done by IIT in the frame of Madeleine, and especially to the platform GEMCO. That would be, so this lecture will be given by Anne Gazex and François Gallard.
Okay, good afternoon, everybody. So we are going to present you the work we did at IRT Saint-Exupéry in Madeleine. And this work consisted in both some methodological contribution and also some developments, some new developments in our software GEMCO that is open source since last May. So my name is Anne Gazex. I am the head of the MDO team at IRT and also a technical skill leader at Airbus Flight Physics. François Gallard is the MDO architect, and he is the initiator of this software GEMCO. And Mathias Delozzo and Jean-Christophe Giré are research engineers at IRT, and they have strongly contributed to all the technical activities we performed. Okay, so what the outline of our presentation? We will shortly present you the context of our approach on MDO at IRT, and then François will present the implementation in GEMCO and the results we obtain, and then we will conclude. So related to the challenge for applying MDO in industry, that's clear that MDO is already applied in academic for years, but still not so well used in industry. And in Madeleine, we have selected a different challenge that are really key to apply it in industry. And at IRT, we have contributed to the following challenge. First, the maintainability of the processes. Since processes are very multiple, there is a large range of processes, and all these processes are also subject to change. So maintainability is really a key issue. And then the scalability is also key, because we have to deal with numerous analysis models, thousands of design variables, coupling variables, constraints, and so on. We have also to think about distributed processes, and at IRT we have specifically worked on MPI processes distributed on many nodes. And obviously there is some mathematical difficulty within MDO, for instance, handling with different types of design variables, but also handling with black boxes and software that can provide derivatives or not. So to be more concrete, what did we do? So firstly, we have developed some optimization strategies as efficient as possible to solve these complex problems. That means including a large number of design parameters with efficient ways to couple the disciplines, and of course, able to minimize the computational cost, which is proportional to the number of simulations and of adjoint computations. And we have been pushed to develop the BLIS 98 formulation to enhance our IRT bi-level formulations family, to apply all these formulations and to benchmark them. Yeah, it's important to develop a different formulation, but also to evaluate them and to be able to select the most efficient one for a given design problem. That's why we have also developed some methodology based on scalable models. It will be explained just after. And then last point is our contribution to accelerate the MDO processes, developing some MPI extensions of multidisciplinary analysis and optimization capabilities in GEMSEO. So what are these MDO formulations first? So the MDO formulations can be seen as templates of MDO processes organization. If a designer has a design problem that you want to solve, this design problem has to be translated within a mathematical strategy that defines a mathematical optimization problem. And this translation can be done in different ways, and the different organization of a process are the MDO formulations. So in GEMSEO, we have coded in advance a range of MDO formulations, and it saves some time for the program, for the designer. He can use some already existing MDO formulation, and this also reduces the maintenance issue. So what should do the designer? He just have to connect, to interface his disciplines, his models to GEMSEO and choose a MDO formulation, and then GEMSEO automatically compute the MDO process. So in GEMS, you will find different MDO formulations, such as the well-known MDF and IDF formulations. So just to remind you that the MDF is based on the coupling phase, where all the disciplines are coupled together, and then upon this coupling, you have an optimizer. And the IDF formulation, you don't have any MDF phase, you just have some analysis in parallel, and the coupling is handled by the optimizer itself with constraints ensuring consistency. And at IRT, we have selected the specific formulations family, that is the bi-level formulations family, specifically well designed to match the industrial processes and tools constraints, because this bi-level formulation reconciles two a priori contradictory objectives. On one hand, we want to create new efficient complex MDO processes. And on the other hand, we also want to take benefit from already existing and well-validated monodisciplinary optimization processes. So on this diagram, you can see that there are three optimizers in parallel. Three optimization problems are solved in parallel at the disciplinary level. And then at the system level, there is an additional optimizer that handles the shared design variables. So this formulation is very flexible, and you can use different optimizers. Some are very well fitting the aero optimization constraints. Some others are more appropriate for structural constraints and so on. But in Madeleine, one of the main objectives is to compute the coupled adjoint. And of course, our objective was also to take the opportunity to use this coupled adjoint at the system level. So we have developed the Bliss 98 formulation that relies on coupled adjoint and post-optimal analysis to compute the gradient at the system level. That is also meant to accelerate the system level convergence. And François will show you the results and how we have applied this formulation. Last point, in our methodological work, we have also thought about the selection of the best MDO formulation. Because since there is a range of possibility, it's clearly not easy for designer, for user, to understand what's the best one for his own problem. And even if he has defined the best MDO formulation for his problem, if he wants to change the dimensions of the problem, the best formulation can also change. So at the end, we wanted to benchmark different MDO formulation as quick as possible. So the idea was to replace each discipline by a scalable model. And then, thanks to these scalable models, to be able to compare easily different formulations. So these scalable models are some models associating the outputs with the inputs, able to give us a very quick answer, and they are built from the evaluation of the original disciplines. But the goal is not to represent in detail the original discipline, but to learn the mathematical features of interest for the MDO process, and then also to be able to be adapted when we change the input and the output dimensions. So again, you will have just in some seconds the results on that. And now I let François explain the implementation.
So I will give more details on the implementations of these different algorithms and their validation. So we have taken the original Bliss 98 MDO formulation from Sobieski and implemented it in GMCO. So we have used coupled adjoint capabilities and post-optimal analysis capabilities together within bi-level MDO formulation in order to be able to use a gradient-based algorithm at the system level. So with the aim of being able to solve a larger scale optimization problem with many shared design variables. So it's a generic implementation. This means it can be used for any MDO problem, provided that the models give the required derivatives. And it's not straightforward at all, because there are many numerical ingredients to be put together within a multi-level formulation, and that also deals convergence difficulties. So then we validated this MDO formulation on the test case provided by Sobieski in the original paper. So it's a supersonic business jet problem, and we could find the same results as in the original paper, and which is the same also optimum as provided by the MDF formulation. So to give, then we wanted to go a step further, and Onera helped us. So there is a strong expertise on the Bliss 98 formulation at Onera, who is working since a while on this. So they provided us guidelines and ideas to improve the efficiency of this formulation. So we see here on this slide the main a view on the bliss ingredients, and especially the main outer loop on the shared design variable. And then at the top, we see the local disciplinary optimization. So they are actually specific because you see a linear approximation as the objective function, and the total derivative of the objective is actually computed from coupled adjoint and coupled adjoint. So we work to use also nonlinear models, so not as in the original variant, to better capture the nonlinear behavior of the disciplines. So using convex linearization or quadratic models, and those the different disciplines can use different submodels for that. We could also add a second MDF phase after the post-optimality analysis to improve the consistency of the coupling. And also, we can replace the disciplinary level problems with constrained non-monotone line searches. So it's a variant of the classical line search, which allows the objective function to increase a bit, but still guarantee the global convergence, and this can provide a more global optimum. Then Onera also provided a specific use case, the wing optimization use case. So it's a dynamic and static optimization, and it's specifically hard to solve by multi-level formulations, because the two disciplines, so static and dynamic, play on the rigidity through the thicknesses in the static optimization, and then this affects strongly the modes, the dynamic modes, and the rigidity of the structure. So a static optimization can destroy all the constraints, the dynamic constraints. So, and this kind of decomposition in between the two disciplines is really at core of the bilevel decomposition. So our original bilevel IRT bilevel formulation failed to provide the right solution in this case. So it's a very good test case to improve the formulation. And we introduced a new variant of this formulation, block coordinate descent algorithm, that is actually iterating over the sub-optimization, so static and dynamics. And it's actually a classical algorithm in domain decomposition applied to optimization. And using that allowed to converge properly. So now I will give more details on the scalable methodology. So as I explained, the objective is to be able to benchmark MDO formulation. So as you have seen, it's a specialty of GMCO to provide many different variants of formulation, but then it raises the question of which one is the most appropriate to a given MDO problem. And especially this choice depends on the size of the problem, so the number of design variables and the number of coupling variables. But we can't benchmark the formulation on real high fidelity problems, and on top of that make vary all those dimensions. This would be way too expensive, and it's not. It wouldn't be usable as a guideline. So the main idea is we replace the original models by an approximation which captures only the required mathematical properties that impact the performance of the formulation. So if you see on the right, the concept is to create a diagonal DOE in the design space, so in an n-dimensional design space. And from that DOE, we hope to capture the main variation and the main non-linearity of the functions, linearity or non-linearity. And from that, we build the 5 functions, which are the basis function for the scalable models. And then so we have many 1D functions, and we want to create a mapping, function that has variable inputs and outputs. And to do that, we combine them linearly. So then the reconstructed function can be seen on the right of the picture. So it's not a classical surrogate model that tries to approximate exactly the function. And also this kind of surrogate can be changed in the input and output dimensions. So this is why also they are inappropriate. And they do not approximate the function, but they capture some properties. So GEMCO allows to automatically build the DOE and generate the MDO process according to these scalable models. Once we have those processes, we simulate a lot of them by introducing randomness in this problem to perform statistics. And we applied that to 2 test cases provided by DLR on the XRF1. So DLR data provided us data for the basis function, the DOEs. And also they provided us the different kind of MDO formulations that they wanted to compare. And same for generic business jet configuration provided by Dassault and ESI, who provided us the DOE data. So then we perform the statistics on the performance of the different formulations by scaling the design variables or coupling parameters, and we provided some guidelines based on those comparisons. So finally, we worked on the MPI extension of GEMCO. So before the MADELEINE project, we could do a parallel calculation by launching CFD calculation on HPC, for instance, and launch several of these calculations with different disciplines, but we could not exchange data in memory between those processes. So this is creating big bottlenecks in the queuing system, for instance, and also performance issues. So in the MADELEINE project, we developed a capability to create a splitting of the MPI communicator and to pass them to the sub-simulation code so that we could exchange processes, information in memory without going back to the queue and performing coupling, very efficient coupling. We also developed the coupled adjoint based on this capability to be able to solve, to compute the total derivatives of the coupled system. And we performed some benchmark on that. So this was a work done also in collaboration with Optimad. We've obtained promising results on up to 250 cores and 5 million coupling variables with coupled adjoint calculations. So then one key aspect of the coupled adjoint also is the numerical efficiency of the linear solver. So it's true for the coupled adjoint and also for the Newton step in the coupling calculation when we use the quasi-Newton algorithm. Before the MADELEINE project, we were using mainly Krylov method based on SciPy, and those were dealing robustness and convergence issues. In this project, there was a lot of effort made on the linear solver resolution. This will be presented just after by Optimad. And we also implemented a wrapper of the PETC solver to be able to use state-of-the-art linear solvers. And Airbus provided us a real coupled adjoint test case based on GEMCO, and we could fix the convergence issue on this stiff problem and get a speed-up factor of 20.
Okay, so let's conclude this presentation. So our collaborative work in MADELEINE clearly offered us several opportunities. So first of all, an increased experience in terms of applying and testing MDO formulations in real applications, a better understanding of MDO formulations and their impact on the performance of the processes and on the optimal designs, and an increase of shared experience and expertise within the MADELEINE consortium. And clearly, we have discussed a lot about these MDO formulations, and together we think that our expertise has really increased in a very interesting manner. In parallel of this work and expertise on MDO formulations, the MADELEINE project was also the opportunity to enrich the GEMCO formulations. So first, we have coded this BLISS 98 with very interesting refinement coming from Onera's expertise. We have enhanced our bi-level formulation engine, enabling to accelerate the convergence. And here it was not planned at the beginning, so it's a very valuable result for us to have been challenged and pushed to develop further our bi-level formulation. And thank you to Onera again for the very interesting test case. It was also the opportunity for us to test in real applications our scalable methodology that facilitates the comparison between different MDO formulations. And this was possible really thanks to this collaborative model of MADELEINE, and realized in collaboration with DLR, ESI, and Dassault. And step by step, we all together understood better how this methodology behaves, I would say. It was also the opportunity to extend GEMCO parallel capabilities and to develop a plugin, a GEMCO PETC linear solver plugin in collaboration with Optimad. And finally, obviously, an increased experience of using GEMCO thanks to Airbus, DLR, Onera, with very interesting feedback, contributing to improve our software. So really, MADELEINE allowed us to take an important step in terms of MDO experience and enrichment of GEMCO with capabilities which are really crucial today for industry. So just to finish this presentation, here you can have a look at the documentation of GEMCO, and you can see also some key elements related to our roadmap under developments. We will enhance the MDO techniques. We'll further develop multi-fidelity MDO, introduce uncertainty quantification, robust MDO, some platform services also, and some other capabilities. And yeah, clearly you are really welcome to contribute if you're interested. So many thanks for your attention. And now, if you have some questions.
Thanks, François. So up to now, there is one question from Stefan on slide 17. Are the many coupling variables handled by the optimizer or in the MDA problem?
So it's a good question. Yes. So in this particular test case, we are doing MDF. So those 5 million coupling variables are handled by the MDA, so not by the optimizer. Yes, but actually this parallelization of the process layer of GEMCO can be used anywhere. So it can be used for also multi-level formulations or even IDF formulations. So we could imagine to distribute the calculation on MPI. Also, the limitation is, of course, currently the optimizers are not MPI parallel, so they cannot be handled, yes, distributed calculation. But one day, maybe this could be imagined to alleviate this bottleneck.
Understood. Thanks.
Thank you for your question.
There is no other question apparently. Except if I do not see them. Dominika, do you see other questions?
I confirm that there are no more questions, Mikael.
Okay.
Okay, thank you.
Thank you.
Thank you, Anne, François. So I propose to switch to the next speaker. So our next speaker is Aizam Telib from Optimad, and he will present some work achieved in the frame of Madeleine on the robustness and efficiency of linear solvers, especially for a joint problem. Aizam?
Yeah, can you hear me?
Yes, we can hear you.
Okay, great.
I can see you now. Fine.
I share my screen. So you can see my presentation, yes?
That's right, yes.
Okay. So good evening, everyone. Thank you for being here also from my side. I'll present the part of the work of Madeleine that was aiming at making things as fast as possible. So in Madeleine, there were two main technical work packages, work package 2, which were, let's say, on the enablers, and work package 3 that was led by Optimad, which was centered around efficiency. And the main contribution in this work package was related to making linear solvers as fast and as robust as possible. So just a second, please. So the outline of my talk, I will a very short introduction, giving some obvious motivations for these contributions, and then I will present three major contributions. The first family of contributions is addresses generic linear solvers. So they are very much linked to what François just presented. So they are solvers that are implemented, for example, in PET-C, or also in by partners of the consortium, but that are not really optimized for a specific task. So they're general linear solvers, and there were some contributions that try to make them faster, to enhance them, etc. A second family of solvers that have been derived in this framework are problem-specific solvers. So adjoint solvers that are really aware of the specific physical problem that we want to solve, and try to enhance exploit some features in the physics in order to accelerate convergence. And finally, I will present also contributions regarding to mesh morphing, where linear solvers also play a major role. And finally, the conclusions and the lessons learned. So, the role of linear solvers. You see, when we are talking about adjoint-based optimization, there are two primary solution steps. So first, the primary equations have to be solved, and afterwards the adjoint equations. The adjoint equations are by definition linear equations. It's a linear system, and so it takes a linear solver to resolve them. This is especially true when we use a discrete adjoint approach. In a discrete adjoint approach, it is the output of the implementation is often really the matrix directly as a linear system. Where often when a continuous adjoint is adopted, there's only the operator available, and so there it is often preferable to use a solver which resembles the solver of the primal equations. But most of the partners in Madeleine, they use the discrete adjoint, And so there was a high interest in linear solvers, in direct linear solvers. Yeah. And finally, linear solvers are also often used in order to propagate surface deformations into the mesh. So they are often part of the kernel of the mesh morphing technology. So, again, we'll see an example how linear solvers can affect the cost of the mesh morphing step. But then there's something very particular to Madeleine. Since we are talking about multidisciplinary adjoint, as Francois already depicted, we come up of a system of systems of coupled adjoints. So adjoint is already a topic linear solvers are already a topic when we talk about monodisciplinary problems. But the problem is even much bigger when we talk about multidisciplinary adjoints. So, the main challenges that we wanted to address in Madeleine, it's related to the cost. So. Real industrial problems can be very big, can be very stiff, and so the cost of the adjoint solver is of primary interest. But of course, also robustness is a critical aspect, because in industrial production, you don't want to need to tune hundreds of parameters to get the efficiency. So the solver should be robust in the sense that the efficiency should be constant over a large spectrum of industrial problems, and without the need of very user-specific calibration. And of course, the accuracy of the adjoint should be guaranteed. That means that we should also guarantee a good level of convergence of the linear equations. All this should be, the maintainability of all this is another aspect, because we often come up with very optimized codes that work very well for a certain problem on a certain machine. But we all know that, for example, the hardware, especially in this period, changes a lot. CPU is still classical x86-based CPU architecture is still dominant, but more and more machines, HPC machines, are equipped with accelerators, GPUs, and making all this development, compliance with this hardware is a big issue. And we tried to address this aspect also in Madeleine. So we also, at the beginning of the process of the project, we had a goal that we wanted to accelerate the execution time of the MDO process by a factor of 5, either by exploiting HPC capabilities, or by optimizing the code, or even by defining alternative algorithms that have better performances. And as I already stated, we were always looking at the maintainability of the code. So now I would like to present you the first contributions that come mainly from Onera and Optimap. And they are related, as I told you, to, let's say, to the improvement of generic linear solvers. In order to do so, a framework has been developed. This framework is mainly divided into two. The lower part is really linear solvers and where the development of the linear solvers took place. And a second part, which is the testing, which is related to the testing, which is actually just an application that reads a linear system from file and solves this linear system. Yeah? So any user could provide the matrix from its from its adjoint code, and we could test the performance of the developments on the actual matrix. So the first contribution from Onera is really on the core of the solver. And Onera, the team at Onera, they exploited the flexible version of GEMRES, which is a GEMRES is a state-of-the-art iterative solving technique. And Onera enhanced it with the flexible version and enhance it with the deflation techniques. These are technicalities that I will not present. I won't go into the details of these approaches because it is let's say on a very deep technical level on linear algebra. But we'll see in a second the results of these improvements. So the test case that they used to validate their developments, it is on a transonic airfoil in a turbulent flow regime. And what is very interesting is that the discretization matrix is relevant to a fourth-order discontinuous Galerkin scheme. So it is not a classical finite volume scheme. It is let's say, a scheme that looks a little bit more towards the future. This is a very accurate scheme with little artificial viscosity. And these schemes are also used, for example, in aeroacoustic computations. The problem, the functional, is related to the minimization of the drag coefficient. And for example, by exploiting the flexibility and the deflation techniques, at the first point, we can see that the robustness of the linear solver can be enhanced. As you can see in this chart, where we see the convergence of the linear solver on the left-hand side versus iterations, and on the right-hand side versus elapsed time, that a classical solver, in this case, for example, GEMRES, does not converge at all. But all the enhanced linear solvers developed by Onera, all of them converge. So they demonstrated that these solvers have an increased level of robustness, and furthermore, you can see how let's say the most sophisticated solver, which is the flexible GEMRES in combination with the deflation techniques, can achieve a speed up around with a factor around 2. In the very in the worst case, the speed up is around 30%. In the same sense, here in Optimat, we worked on the preconditioning of these matrices in order to see if by enhancing the capabilities developed by Onera, we can even push the efficiency further by developing preconditioners that are as efficient. We try to have preconditioners that are as efficient as possible as the direct solvers. They were inspired very much, but the optimizations that we have in the direct solvers. So this was tested on a different case. It is a laminar flow of a NACA 0012 profile but the data were provided in this case again by Onera. What has been done is that within the matrix we find degrees of freedom that are very strongly linked. And for example, in this case, working directly on the data, we find degrees of freedom that are linked through the mesh, through the stretching of the mesh. Excuse me a second. Sorry for that. And in the preconditioner that we developed, we try to exploit these links. All this has been this contribution, this pre-processing of the matrix has been done by has been developed by Onera, and it has been implemented on top of the PETSI library. The exploitation of this information resulted in a speed up, again, in a factor of, with a factor of nearly 2.5. Where we use an algebraic multi-grid strategy that exploits the information extracted by Onera from these matrices. Combining these two strategies, we could expect an speed up of around with a factor of 4. The next contribution that I would like to present you, it comes from NLR. And we will see here how, let's say, specific adjoint solvers for specific problems can achieve very high gains in efficiency. In this case, NLR was dealing with periodic flows, like the ones that we find for turbo machinery and propellers. So periodic flows can be categorized in two groups. One is you have a periodicity in one blade passage that is exactly in phase with the flow of the adjacent blade passages. So what is happening in one blade passages at a certain time is exactly the same thing that is happening in the near blade passages. In this case, standard periodic boundary conditions are used both in the direct and in the adjoint solver. But what NLR enhanced this strategy even to flows where there is a phase lag between adjacent blade passages. So what is happening in one blade passages is exactly the same thing that happened in the previous blade passages some time ago. So by exploiting this information, they derived an ad hoc boundary condition, which is called the chorochronic boundary conditions, that allows them again, to simulate just one bait passage. So in this case, the reduction of all the computational footprint, that means storage, input, output, and CPU time, is equal to the number of blades of the stage. For example, for this case, the stage is composed by 22 blades, and so they experience, let's say, a speed up of a factor of 22. On the right-hand side, you can see the validation of this technique by, in green, these chronochromic boundary conditions, and in red, the full unsteady adjoint. You see that there is a perfect match. The last contribution that I want to present you is related to mesh morphing, because also mesh morphing, let's say, in a lot of mesh morphing technologies are based on linear solvers. And in particular, when RBF stands for radial basis function, is one of the standard techniques today in order to perform mesh deformation, because RBFs are graph-free interpolation methods. That means it's a technology that does not depend on the topology of the grid. It works for any kind of grid, and the only thing that matters is the correlation between the surface nodes, where deformation takes place, and the vertices in the volume grid. But RBF can be very, RBF-based mesh morphing can be very, very expensive. In order to do RBF based mesh morphing, there are two tasks that need to be performed. The first one, it's an interpolant needs to be calculated, and this calculation it's in the end the solution of a dense linear system that has the dimension of the number of surface nodes. So in an industrial case, the number of surface nodes is of the order of hundreds of thousands, and solving a dense linear system of this dimension is still a problem today. The second task in RBF-based mesh morphing is then applying this interpolant. This is a problem really due to complexity, because in order to do this interpolation, in order to displace each of the volume nodes, all of the surface nodes needs to be visited. So that means that if we have a computational mesh that has the orders of tens or hundreds of millions of volume nodes, and a surface mesh of the order of hundreds of thousands, we come up with 10 to the 12 or 10 to the 13 operations, which costs really a lot, which is a huge number. And furthermore, the complexity of this algorithm, that means the law that tells you how the cost scales when you, for example, double the mesh, is very high. So it means if you go, for example, from a coarse mesh to a medium mesh, and you have a factor of 10 in the number of cells, this algorithm will cost you 50 times more than on the coarse grid. If you go, if you have a factor of 100, it will cost you 2,500 times the original cost, which can be prohibitive. And so to this scope, for example, in this case, N2A developed a very promising algorithm that decomposes the let's say this global system into two parts. First, into a global sparse contribution, and then a local dense correction. Again, I won't go into technicalities, but with respect to the state, let's say, with respect to the RBF implementation before Madeleine, they achieved a speed up of more than 10 for the cases that have been addressed in Madeleine. But what is even more important is the reduction in complexity. So when we have to deal with a big problem, the cost will not explode as in the original algorithm. And this can be seen in this graph, where you can see that as the size of the problem increases, the optimized version of the RBF morphing technology remains nearly constant. So, so this is really a remarkable achievement. So now I'll switch to go to the conclusions. So within Madeleine, we tackled some very challenging problems regarding the efficiency of the MDO process. We could achieve important speed ups in both solving the adjoint equations and also in making the mesh morphing techniques scalable and compliant with large industrial problems. As you maybe noticed, the most important speed ups that we achieved have been introduced by really by domain experts and people who really know around the physical problem. So this, whereas when we worked on a general framework, the speed ups were a little bit more moderate. And this issue remains a little bit a problem because, for example, if you want to move towards the next generation of architecture, where, for example, we have to be compliant with heterogeneous computing, that means CPUs plus GPUs, these kind of implementations are more demanding. So for sure, there is still space in order to try to have to develop frameworks that take the best of the two worlds. And that's it. Thank you very much.
Thank you, Aizam, for the presentation. We have one question from Norbert Kroll from DRR. Do you see strong dependencies of the adjoint solvers with respect to the accuracy of the primary solutions, in particular for more complex applications?
I beg your pardon, Michele?
So,
strong dependency of the adjoint solver from the...
So, do you notice a strong dependency of the adjoint solver with respect to the accuracy of the primary solution, of the primary solver?
Of course, there's the accuracy of the, also the accuracy of the adjoint with respect, if the primal solution is not well converged, is for sure an issue. We know about this. I must say that we did not look at this topic within Madeleine. So when we were working on the adjoint solvers, the matrices came from well converged primal solutions. But we know that, for example, that in the test case that has been addressed by Onera, where we have a complex flow and a complex discretization, high order discretization, that often lead to non-well converged primal solution, that, for example, classical linear solvers do not converge. So, so we know we have a trace of this issue, but we did not address it directly in this project.
Another question from Marcus. How do you set up a space-time boundary condition, chronic, regarding mesh generation, or can it be arbitrarily modeled?
Well, this the colleagues from NLR should respond to this question. But you see, from a geometrical point of view, it is the same thing as a classical periodic boundary condition. What you have to take care of is that you don't, if you once you need the solution from the other side, you have to pick it not at the same time level, but you have to pick it in the past. So if you can, handle periodicity with mesh morphing, and if you have this kind of technology, you should have all the primary ingredients to implement these boundary conditions.
Bang Bang, do you want to add something on this, as these many activities from NLR? Bang Bang, we cannot hear you. I see that you're unmute now, but I cannot hear you. So maybe just another word. So just a remark on the chat also from Ralph Heinrich. Remark on RBF, at least in case of elasticity, you do not need each surface node for the wing. You can simply reduce the number of nodes to 2,000 as long as the change of the geometry is smooth. But just a remark regarding the
of course,
mesh morphing. So last try with Bang Bang. Bang Bang, can you just speak, maybe? No, we cannot hear you. Sorry. So any other question among the participants? If not, I think we can close the session for today. First, I would like to thank all the speakers for your nice presentation. And we will continue. So tomorrow morning, we will start at 9, exactly 9. So please, if you want to attend, connect some minutes before to ensure that everything will be fine. So thank you to all participants for the attendance today, and I hope you will join also tomorrow, where we have 6 other presentations with on different topic. So very also interesting, I think, presentation. I can maybe just remind you and share the program for tomorrow. Yeah, so tomorrow, yes, we'll have 6 presentations. Regarding model-based system engineering, uncertainty quantification, fan blade design, thermal manufacturing, turbine blade design, isolated propeller design, and aeroacoustic fan blade design. So thank you for your participation, and I hope we can continue to discuss tomorrow.